So did you see that slide advance?
Yeah. Yes.
Okay. So I wanted to basically help focus the talk with a few questions. I'm going to be talking about Laramide Shallow Subduction beneath the Southern California region. One of the key aspects of this is, first of all, when was it initiated? In terms of the rates of the process, when did the most rapid subduction refrigeration related to underflow of cold oceanic crust occur? We want to be able to see if we can differentiate in terms of the overlying rocks, the magmatic arc, if we can differentiate between erosional and tectonic denudation. And finally, we have a significant record in the Four-Arc Basin from the Laramide Shallow Subduction event. We want to ask, where did this sediment originate for the most part? So I have an outline for you. Some of these topics are pretty short, and I'll try to adapt as is possible, given the goals here. The first thing is one of the most prominent features of subduction is obviously the heat flow anomaly that's associated with it. And so here I'm showing the Cascadia subduction zone in Northern California, Oregon, Washington, into southern British Columbia. And it's very obvious where the subduction trench is, and the very cold heat flow that you see here. This image is basically cast in terms of the estimated temperature at approximately 10 kilometers depth. So this is adapted from Blackwell et al. 2011. And it's an interesting perspective because we're going to be talking about deep crustal processes. And so during normal subduction, we have the pattern that you can see here. But during flat slab subduction, where in particular, when the subducting oceanic lithosphere is being shallowly subducted beneath the margin, the heat flow anomaly is shifted to the east, and once produced is a very long-lasting feature. And so, if you can see here in the Sierra Nevada region, the Great Valley and Sierra Nevada region, right in here, there have been subnormal geotherms persisting throughout this region that survive today, with temperatures as low as 100 to 150 degrees C beneath some parts of the Sierra Nevada batholith. So we're going to talk about how this formed and try to interpret some of the details of this. In particular, we're going to be using a lot of thermochronology to help us interpret the heat flow in this situation. Most of you are used probably to interpreting thermochronology in terms of approach to the surface. But when we have shallow, flat subduction, we have an additional heat sink, and that's the subducting oceanic crust. So we can cool from both above and below. That introduces an ambiguity that we're going to try to get some additional control on. And so now I'd like to just point out some of the gross aspects of the late Cretaceous earliest Cenozoic Laramide shallow subduction event. It's related to the fact that the Atlantic Ocean has been opening up throughout the Cretaceous and to present day time. And this has caused westward drift of North America toward the Pacific domain. At the same time, you can see in this North America fixed reference frame during the Cretaceous, all the way into the earliest Cenozoic, the Pacific, in the Pacific domain, the Farallon plate has been subducted beneath Western North America, and the rates of underflow at this time approach on the order of 150 kilometers per million years. And so that's the general overview. There's a huge amount of data that's been amassed throughout the years. This is a review paper by Peter Copeland and others, basically combining a lot of different types of data, including the ages of magmatic rocks, marine deposits that are related to the development of the flat slab geometry, shortening in the upper plate, in the middle of the continent, and in particular, shown here in this cyan triangle is the progress as a function of distance and time of an additional topography on the subducting oceanic slab, what's believed to have been a large oceanic plateau. And so the trace of this is shown in this diagram from Liu et al. In 2010. The initiation of the flat slab subduction is believed to have corresponded with the advent of the conjugate of the Shasky rise, which is in the West Pacific region. So on the Farallon plate, its conjugate is believed to have arrived at the margin shortly after approximately 90 million years. And in approximately 20 years, this feature has been subducted to the map position of South Dakota. And so this represents approximately 2,000 kilometers of underflow in 20 million years, or on the order of 100 kilometers per million years. This conjugate feature to the Shasky rise is thought to be a very large feature, 500,000 square kilometers in extent, a lateral dimension on the order approaching 800 kilometers or so, and involving oceanic crustal thicknesses up to 17 kilometers. So in a shallow subduction event, this is believed to have had a massive impact. And so just briefly, without getting into the details, the timing of all this has been basically worked out through plate reconstructions shown here on the left, and also looking at mantle tomography and restoring this mantle tomography as a function of time. Most people, when they think about the Laramide, are thinking about the deformation that's occurred in the well within the continent, in the Rocky Mountains and so forth. And this is probably appropriate, but since given mine and my collaborators' interests on what's happening on the margin, the focus on this talk is going to be almost exclusively on the Southern California margin, including crust that's been displaced to the north along the San Andreas and related faults throughout the Neogene. So shown here is a pre-Oligocene or pre-San Andreas palinspastic restoration of the Southern California region. And the Laramide deformation has had a significant impact on this region, shown here between the southern Sierra Nevada batholith and the northern part of the peninsula ranges. Most of these rocks here are now a part of salinia that have been displaced to central California. But you can see that to the north and to the south, the magmatic arc has an asymmetry to it with a well-developed mafic western domain and a more felsic eastern domain. This has been a widely acclaimed feature of these batholiths going back many, many decades. In the Selenian region, really only what we have in terms of the magmatic rocks are the eastern facies. As you get up toward Point Reyes and Bodega Head Bay and other areas, you start seeing more typical rocks from that characterize the mafic western domains of the Sierra Nevada and Peninsula Ranges batholith. But for the most part in Selenia, you see relatively evolved rocks. In particular, you have magmatic arc rocks juxtaposed in some places directly against the subduction complex. And elements of the forearc have also been greatly attenuated. And by some estimates, and of course this involves a lot of guesswork and assumptions, we're missing approximately 100 to 150 kilometers of the forearc and batholithic region in the Selenian region that restores back to the Southern California area. So what I'd like to do now is basically present some of the major conclusions that we can derive from accreted trench-derived sediment that was subducted beneath the Southern California region and then exhumed to the surface during later tectonic events. So again, this is a palinspastic restoration of the Southern California region. And this is an interpretive cross-section from the Sierra Nevada going from north on the left side of the diagram toward the Mojave region in the south. So the Garlock Fault is located approximately in this location right in here. And based on a large amount of seismic reflection data and petrologic relationships that are present in the southern Sierra Nevada, it's interpreted that we have an oblique section of the batholith that increases from typical crustal erosion depths in continental margin batholiths of 2 to 3 kilobars depths, or on the order of 7-8 kilometers maximum erosion depth, all the way up to nearly 10 kilobars or approaching 30 kilometers. Directly underneath these rocks, and we find a metamorphosed sediment. In this case, in the southern Sierra Nevada, it's referred to as the Rand schist. But this material is found throughout the Southern California region in different geographic localities. It's given different names: the Pelona Orocopia schist, probably familiar to you. In the Selenian area, we have the Schistus the Salinas. There are a lot of common factors or observations that you can make for all of this. Nearly 90% of this underplated schist that we find beneath the mid-Cretaceous continental margin batholith, including as far east as Arizona beneath the Craton, nearly 90% of this material is basically trench fill, quartzo-feldspathic, metasandstones, and shales. There's approximately 10% of this material that appears to be mid-oceanic ridge basalt chemistry. There's a little bit of serpentinite. Usually it's highly silicified. Actinolite schists are common when you find the silicified serpentinite. And there's a smidgen of chert marbles and other lithologies that are generally associated with the mafic rocks. In terms of metamorphic grade, most of this material is basically in the high pressure green schists. Locally, there are some epidote blue schists in the Rand Mountains, for instance. And structurally high in these sections, you'll find epidote amphibolite, garnet amphibolite lithologies, but they're not very common. So what I'm going to do is take this restoration right in here and strip away all the rocks that are in the upper plate. And in the lower right-hand corner, shown in blue, are basically all of these subduction-related rocks that are associated with the Laramide Shallow Subduction event. And so these are palinspastically restored. I've just sort of arranged them from northwest and the southern tail of the Sierra Nevada batholith, the San Miguel Mountains, all the way down into southwestern Arizona, where we have the Trigo Mountains, Castle Domes, and some newly discovered locations. And so the amount of area that's known to be underlain by the schist is approaching 100 kilometers squared. We're not sure about the rest of the Southern California region, but potentially it's even greater than that. When we look at this diagram, one thing to realize is that in the northwestern part that we're going to be primarily focused on in this talk, the schists are underplated, juxtaposed beneath mid-Cretaceous arc rocks. But when you get down into the southeastern area in southwest Arizona, the schist is basically juxtaposed immediately beneath the craton. And so this configuration allows us to have on the order of about 250 kilometers of oblique view or information that we can derive from these underplated schists. I just want to briefly summarize some of the results. A lot of this took a long time to accumulate. This is summarized in this Jacobson et al. 2011 GSA bulletin paper. And shown here on the left are detrital zircon uranium lead age distributions from various schists. So the San Miguel are the northwestern most of these. They have an arc provenance. It looks pretty much like the provenance signature of the Sierra Nevada and Peninsula Ranges batholith. And progressively younger schists, the Rand schist, the Pelona schist, and the Oricopia schist, underplated beneath southwestern Arizona. The youngest zircon becomes progressively younger, and you start to see greater quantities of cratonal materials. So, for instance, there's a lot of Jurassic, some Permo-Triassic, and a lot of mid-Proterozoic cratonal-derived material. So on the right, what I've done is I've taken these distributions right in here, and I've superposed them on coeval rocks from the Southern California forearc. And as you can see from this collection of data right in here, the schist in this oblique section from the southern Sierra Nevada into southwestern Arizona is accreted or appears to be accreted at progressively younger times. And as it's accreted, it's becoming more cratonal through time. And finally, the sediment that carries the same provenance signature as the accreted schist is present in the Southern California forearc region. In other words, when we require a certain composition of sediment to be transferred to the trench, we can document that the sediment of a given age has the appropriate provenance signature. Another thing that we can do with this data is that we can basically constrain the time required for material derived from the hanging wall or the magmatic arc to craton to be eroded, transported to the trench, subducted, and accreted. We call this the cycling interval. And on this diagram right in here, it's indicated by this yellow shading. So it's constrained by the detrital zircons that the schist contains. This puts a maximum bound on the cycling interval. And it's also constrained, particularly in the southeastern region, by metamorphic zircon growth, and finally by thermochronology results from the schist. And so as you can see, most of the action here is occurring between the southern Sierra Nevada and the transverse ranges, the San Gabriel Mountains and their equivalents in southeastern California. And so there's on the order of about 15 to 20 million years between the time at which we first see accreted schist beneath the magmatic arc and when it reaches the central and eastern parts of Southern California. And so right now I'm just going to say a few things briefly about the kinds of tools that we're using right in here. Some of you may be familiar with the concept of a cooling age. We can give a kinetic significance, a temperature significance to these if we have diffusion data from the mineral that's hosting the daughter product of that we use for thermochronology. And we also can work out the kinetics of how rapidly, as a function of temperature, a daughter product like argon, which doesn't want to be in the crystal structure of a silicate mineral, can be released to the intergranular region, ultimately to, say, a fluid or a melt phase, and ultimately to the atmosphere and outer space. Argon doesn't want to be in minerals. And so if we can calibrate this, we can do quite a bit. I'm going to be working almost exclusively here with potassium feldspar. And one of the reasons is that potassium feldspar is anhydrous. And so it's stable under heating. This is important because we extract the argon in a vacuum. And so a hydrous phase is decomposing as you heat it, whereas K-feldspar is more robust. Even more important than that is that K-feldspar has a rich array of microstructures that basically cause the ability of K-feldspar to retain radiogenic argon to be variable. And we could take advantage of that by performing incremental heating experiments in which we develop not only the age spectra shown here on the left for a potassium feldspar, but we also calibrate the diffusion properties of the material at the same time. And from this information, we're able to basically invert the argon 4039 data and calculate under favorable circumstances when our assumptions are met a cooling history. And so the most favorable situation is when temperature decreases monotonically in the crust. This approaches a unique solution. When temperature is variable or could increase in the crust, this introduces a lot more uncertainty. So finally, we've developed new methodologies for extracting argon. We're now using diode lasers, which heat a very small foil packet on the order of about 3 millimeters. So we have this micro furnace that we can extract the argon from. It's all computer controlled, and we've actually dispensed with step heating we use a ramp heating approach, and we've been able to demonstrate that we understand the diffusion situation in the experiment sufficiently well that we can, reproduce the kinetic and age information that we were able to obtain using older technology. So now I'm going to show you some of the data. It's going to be presented in most of it in a highly interpreted form. I apologize for that, but this talk has to be short. So the first thing I'd like to show you is the general characteristics of cooling age distributions throughout the batholithic rocks of the Southern California region. And so shown on the left here is an age contour map in which potassium argon and argon 4039 total gas ages from mineral biotite are being shown. And so ages that are older than 105 are shown in the darkest blues. Ages that are basically early Cenozoic are shown in red. And everything in between is on this color scale right in here. And so you can see both the Peninsula Ranges batholith and the Sierra Nevada batholith have a strong age zonation in terms of biotite cooling ages, from ages that are approaching 100 million years down to 90 in the West, and much younger ages down into the 70s, and in the case of the Peninsula Ranges, even into the high 60s in the East. Mojave region resembles the eastern part of the Peninsula Ranges in that it's generally somewhat younger. And what I've shown here in this section XX prime right in here are in red are crystallization ages from uranium, lead, zircon dating results, showing that there's also a crystallization age trend from the western part of the batholith to the eastern part, as shown here, and that the biotite and potassium feldspar, shown in these blue circles right in here, are generally on the order of about 10 to 20 million years younger than the crystallization ages. So these relationships have been known for a while. What we're going to do is develop more information from the dating experiments so that we can calculate thermal histories. And so here's an example. Our sampling is shown here on the left. There are on the order of approximately 115 samples shown in this database right in here. And for each of them, we've measured an age spectrum, and we've measured the diffusion properties of this material. And from this information, we've calculated part of a thermal history. We're only able to recover the part of the thermal history that's recorded by, in this case, potassium feldspar. And so here the age spectrum basically is between approximately 79 to about 83 million years. But as you can see, it records a pretty significant cooling from approximately 350 degrees down to about 150 degrees. And this is typical of many or most of our samples. And so what I'm going to do now is basically, I'm going to represent these thermal histories in this map to the on the left, or sorry, the right-hand side of the screen. And so temperatures that are greater than 350 are shown in red. So at 90 million years, only a small part of the western part of the southern Sierra Nevada has begun to cool beneath 350 degrees at 90 million years. The eastern part of the batholith continued to be emplaced. In fact, there's Pluton emplacement all the way down to approximately 85 million years. And so part of the reason why these rocks are not able to cool is that there's still active intrusion, at least down to approximately 85 million years. And so orange is basically 300 to 350, yellow 250 to 300, and so forth, right in here. So what I'm going to do is step forward through a number of time slices. So this is 90, this is an 86. You can see basically a lot of cooling has started to happen now in the western part of the batholith. This feature right in here is part of the Kern Canyon fault zone. This is the San Andreas Fault and the Garlock Fault shown in right in here. So by 82 and 78 million years, we have a very strong contrast developed across the Kern Canyon fault zone, whereas most of the samples that are in the southeastern part of the Sierra Nevada are still above 350 degrees. Some are in the 300 to 350 range, and virtually all of the Mojave is remaining above 350 degrees. Here's 74, 70. By 65, most of this region has cooled below 150 degrees. And as I mentioned in the introduction, parts of the Sierra Nevada are believed at 10 kilometers depth to be somewhere between 100 to 150 degrees today. So if it was 150 degrees, that would be a geotherm of 15 degrees C per kilometer. So the geotherms are still not recovered from the shallow subduction event. So by 60 million years, there are only a few places where the rocks are remaining hot, and they're generally located along the Garlock Fault, as you can see, this area. So this would be the Rand Mountains. The Garlock Fault is a left lateral fault. So if we restore that slip, these red circles right here would restore back to the Rands. So I'd like to focus briefly on the Rand. So here are the Rand Mountains. Here's the Garlock Fault. Basically, Highway 58 is coming through Tehachapi region right in here and going through Mojave. This is 395 going off to the Eastern Sierra. And what I'd like to do is show you some results, just a couple results from the hanging wall of the Rand Mountains, where we also have Rand schist exposed. So here's a couple samples. AG1A is in this location. BG1 is basically right on the contact. In between the hanging wall, the Atoya granodiorite, which is approximately 87 million years old in this region, and the Rand schist is generally a very thin tectonic unit referred to as the Johannesburg gneiss. And as you can see, the age spectra that we're measuring from these rocks are much, much younger than you see anywhere else in the Mojave. If we were to integrate all of these results into a total gas or potassium argon age, these samples would have total gas ages on the order of 30 to 40 million years, or maybe even younger. And even more importantly, what they're recording is a significant amount of time in which these rocks in the Rand Mountains are residing within the middle crust. What I'd like to do now is compare the results from the Rand Mountains, where we had the upper plate, granodiorite, Atoya granodiorite, in place at approximately 87 million years ago. Its thermal history is shown in red, and some of these thermal history results that I've obtained from potassium feldspar are also shown in red. So as you can see, we have a number of tectonic units in here, a stack series from the underplated Rand schist all the way up to shallower parts of the overlying continental margin arc. Shown in gray are results from the underplated Rand schist. And so here we have detrital zircon results. They put a maximum bound on when the sediment that was subducted and accreted to the base of the present-day Rand Mountains reached the trench. The peak time of metamorphism, underplating here, is on the order of about approximately 77 million years. Then you can see the rocks cooled relatively slowly throughout this time. So this definitely represents one of the deepest structural levels within the Mojave. Shown on the left, alternatively, are results from the San Emigdio Mountains. In other words, the southwesternmost tip of the Sierra Nevada batholith. And again, I showed you earlier, some of these rocks are quite deep, at least at the time of crystallization, with depths in the range of 20 to 30 kilometers deep in the crust. And they are basically juxtaposed directly above Rand schist in this location as well. What you should immediately notice is that these thermal histories for these two regions are significantly different. The San Emigdios, the schist is accreted sometime between 91 to 88 million years. In the Rands, it's somewhere between 79 to 76. The San Emigdios are basically approaching the surface and have deposition of marine sediments of early Eocene age and potentially even late Pliocene age in the Tehachapi area. So basically they were approaching the surface somewhere around 60 million years and had marine sediments sitting on top of them. In the case of the Rands, the first indication that we see that the Rand schist has approached the surface is basically in late Miocene sediments surrounding the Rand Mountains. So significantly different histories. I'd like to be able to understand this. So the first thing to recognize is that in terms of the timing of accretion, the data are not hugely precise, but something in the neighborhood of at least 10 to potentially 15 million years difference in the timing of accretion relative, over a distance that's approximately 40 to 50 kilometers. And so when I mentioned earlier in this talk that the shallow subduction event was thought to have been triggered by subduction of a large oceanic plateau that was basically being subducted at a rate that was approximately, an average of 100 kilometers per million years, it's kind of hard to understand why the time of accretion in this region can vary so significantly over a much smaller difference. So in 10 million years, you have 1,000 kilometers of underflow. Here we have 15 million years, and it really looks like not much is happening. So we'd like to try to understand this a little better. And so now I'd like to try to obtain some insights into some numerical simulations of shallow subduction. This is work by Claire Curry, and Peter Copeland has been one of our long-term collaborators here. We're not going to get into the details of this continent scale calculation that they're doing here. Although, if you're interested in what causes the shallow subduction or the shallowly subducting oceanic lithosphere to eventually start to dive into the asthenosphere, the timing and nature of the basalt to eclogite transition is pretty critical. But in fact, we're going to have a very myopic view relative to these calculations. And so here, this inset, we're only interested really in what's happening in the upper 60 kilometers. And so we're going to be focused on this yellow region right in here. And these are some results that Claire calculated for me, that just focusing on the upper 60 kilometers of the crust. This calculation, of course, is numerical. And so I've assigned the geologic significance of 80 million years for the time at which the plateau oceanic plateau is entering the subduction zone. You can see it's lurking right off in the edge right in here. Let's get a focus on these two yellow points right in here. I'm representing the Sierra Nevada batholith in a crude way by this red rectangle. And these two yellow circles are separated by 50 kilometers. And so at 80 million years, both of these are 10 to 30 kilometers above the subduction zone. At 60 million years, well, let me explain a little bit more. The upper crust right in here is represented by yellow. The lower crust is represented by green, and lithospheric mantle is represented by light gray. And so as we go from 80 million years down to 40 million years, which is approximately the duration of the Laramide orogeny, what you see in these calculations, which allow the rocks to deform, it's a plastic deformation, Arrhenius type scaling for the mechanical properties of the rocks here. What's happening is that there's subduction erosion of the lower crust occurring in between 80 to 60 and the lithospheric mantle. By 40 million years, there is almost no lower crust in the red box. And you can see lithospheric mantle is way off onto the end of the right. Now, this is post-subduction down in here after 40 million years. But one of the big insights in terms of why it takes so long to have underplating beneath the westernmost or southwesternmost Sierra Nevada batholith in the Rands, which are in the eastern or southeastern part of the Sierra Nevada, is basically there has to be a lot of subduction erosion occurring to allow this juxtaposition to occur. And so, just for the sake of argument, I have used argon diffusion parameters, the same argon diffusion parameters for both of these circles, so we compare apples with apples. In the lower left-hand diagram right in here, this is a thermal history that's calculated from Claire Curry's model. And I show a solid red segment here until 65 million years. And then I dash the rest of this history to show two different potential paths. One path is that basically we stay isobaric. We stay at the same level of the crust. Of course, we would never see this sample. And the second situation or scenario is which we basically rapidly erode or tectonically denude the continental margin batholith, such that we basically have rocks that were originally at 20 kilometers depth at the surface by 60 million years. This is just a cartoon. There are many other calculations that could be shown. But the one thing I want to emphasize here is as soon as Laramide subduction stops, you see the rocks start to heat up. They don't start to heat up very quickly, but they start to heat up. And this has a dramatic effect on if we could recover samples that were 20 kilometers deep in the crust, what their age spectra would be. So shown here on the right is the age spectra of the sample, which is on the western margin of the, or the western portion of the Sierra Nevada batholith. And shown in red are results for the eastern part of the Sierra Nevada batholith. And so if we calculate an age for these results right in here, for the western batholith, we'd calculate an older age, 81 million years. And for this result right in here, we'd calculate 68 million years if we denude the rocks during the Pliocene. However, if we just let them stay isobaric, the less retentive parts of these cave feldspars are not going to be able to retain any argon at 20 kilometers depth, given since they're experiencing to 200 to 300 degrees Celsius temperatures. And so this is another important inclusion, that there needs to be some exhumation of the Sierran rocks and their Mojave equivalents during the period of time when we're experiencing subduction. So what I like to do now is take another view of this. I've been working entirely with basement rocks. What I'd like to do now is look at some sedimentary rocks that we believe are detritus derived from the southern Sierra Nevada and the Mojave region. And we're going to apply two different types of observations. We're going to do the same kind of measurements that we perform for the basement, but we're also going to measure their lead isotopes. So cave feldspar loves to retain trace amounts of lead. You can have, tens of ppm of lead in cave feldspar. So even though it doesn't like argon at all, it accepts lead into its structure. And this is going to be useful in terms of assessing the provenance. And so this is just some of the work that we've done on this problem. But we're going to be looking at sedimentary rocks that are sitting directly on top of the southern tail of the Sierra Nevada batholith, and rocks that were formerly adjacent to them prior to San Andreas offset into towards central California. And so these would be the Eocene rocks of the San Amigdios, would include the Uvis conglomerate and the San Amigdio formation, which is upper Eocene. Uvis conglomerate is lower Eocene. And also rocks from the Butano formation, which are in central California today. We're also going to show some rocks from materials that are basically derived from erosion of the western Sierra Nevada. So this would be north of Bakersfield Arch and here, the Point of Rocks formation, right in this region. And so there's a lot of stuff going on in this diagram. Shown in magenta are the distribution of zircon, uranium, lead crystallization ages from the Sierra Nevada batholith. There's various sources for this compilation. This histogram shows all of the basement cave feldspar thermal history results expressed as total gas ages. Notice that there's a peak of 75 million years, and it's offset by 15 to 25 years from the peak times of crystallization in the Sierra Nevada batholith. This is a cumulative plot in which we basically integrate this histogram to get a cumulative distribution. And so the basement results here are shown in black. Shown in red are results from the San Amigdio and La Honda Basin. I've summed them all up together. And if we looked at the corresponding histograms down here in the lower left, you can see that they basically have a maxima somewhere in the neighborhood of about 80 million years, 79, 80 million years. It's a little bit older than that which we see for the basement, but that makes sense, right? because the basement is exposed today. It's the present day erosion surface. And these materials shown in red were derived from older erosion surfaces in the Sierra Nevada. So they should be somewhat older. And then shown here in blue are results from K feldspars that are fed exclusively from the western face of the Sierra Nevada batholith. And so you can see they're just barely resolvable from the southern Sierra and western Mojave derived materials in the San Emigdio and the in the Butano formation. And so if you look at this diagram, even though subduction and underflow, are thought to start somewhere around post 90, maybe 90 to 88 million years. And it takes a lot of time, 77 million years before we have any evidence of accretion, subduction accretion beneath the eastern Sierra Nevada. You can see that the main phase of cooling that's associated with this event is basically, centered around 80 million years when you look at the sediments and 75 million years when you look at the basement. That's a fundamental result. We actually can take these single crystals of K feldspar and heat them up just like we can the basement K feldspars and calculate thermal histories. The data are a little messier. What I've done here is I'm just considering the statistical averages. So shown in solid line here would be the median, and the plus or minus 90% confidence intervals are shown in these dashed lines. If we basically take the derivative of this, we can calculate the cooling rates, and we can see basically for the K feldspar is even though the total gas ages have a maximum of close to 80 million years, the peak time of cooling is closer to 75 million years. So finally, and I'm almost done, we're going to look at some results from lead isotopes from the same materials. Whoops. And so the first thing we did was we characterized the southern Sierra Nevada and the Mojave region. The southern Sierra Nevada and the Selenian block right here, you can see have a much more restricted distribution of lead isotope ratios relative to the Mojave region. And this has been well known. What I'm plotting here is 208, 206 versus 207, 206. So this is a plot that you might not be familiar with. What I'm going to show now are results from the sediment. And so almost all of the sediment here, a Miocene sample here from the Tumbler Formation has a relatively restricted distribution, but all of the Eocene units have a much broader distribution evocative of derivation from the Mojave region. And in fact, we've quantitatively evaluated this by taking our data and binning it and going into progressively larger and larger catchments to the east or to the north, right in here. And the best fits that we get to our lead isotope data basically have material being derived from as far east as the eastern Mojave region, approaching the southeastern California area. So what we've demonstrated with this is that these K feldspars are exactly the same K feldspars that we use to do these calculations with here. So I'm ready to reach some conclusions. We had some questions. I could have asked a lot more questions, but here's some take-home information. When was Laramide's shallow subduction initiated? It appears that at the southern end, southwestern tail of the Sierra Nevada, we have evidence that it was occurring, initially occurred somewhere in the neighborhood of about 90 to 88 million years. it took a long time for this process to occur as we went further to the east. So the eastern Sierra Nevada batholith, we have evidence of accretion at approximately 77 million years. And I've attributed this to subduction erosion. You can't accrete those rocks until you've removed the lithosphere, subcontinental mantle lithosphere, and the lower crust. And so the most rapid subduction related cooling also occurred during this interval, 80 to 70 million years. I want to say a little about tectonic erosion. We have a big tectonic break in the Sierra Nevada along the current canyon fault. And this has been known from lower temperature thermochronology, uranium, thorium, helium, and Fischer-Trak work. But we can document that this discontinuity existed during the late Cretaceous between approximately 78 to 70 million years. And this is evidence of tectonic denudation in which the parts of the Sierra Nevada are basically being displaced by some sort of normal faulting attenuation to the west. This is an idea that Jason Salibi and Alan Chapman have been pushing for over a decade. And so we have evidence in support of that. And finally, most of the sediment, or a large portion of it, is derived from the eastern part of the Sierra Nevada batholith in the Mojave region. And so the western part of the batholith, which was represented by, say, the Point of Rocks results that I showed you in the Eocene, isn't really manifested to any extent in the sediments that are clearly, showing the Laramide cooling. And so I'd be happy to take questions at this point. I'll leave the share up in case we need a slide. I hope I didn't go over your scheduled time.
That's fine, Marty. Thank you very much. If people would like to ask questions, I'll have you come up and use the mic. It's a lot of data here. A lot of different things were presented today.
Yeah, unfortunately, I collect data.
This is Will Schweller. I actually have a history of studying subduction zones along South America. But one of the aspects of tectonic erosion that might relate to your subduction of that overly thick oceanic platform is that you don't get accretion of a sedimentary prism when you don't have sediment. That happens in the middle of northern Chile. So if you're actually impacting a thick slab of oceanic crust, you're probably actually not having a trench that's capable of accumulating much trench sediment. So by that definition, you're not getting much, and that might actually initiate the subduction erosion underneath the prism, the previously accreted prism.
Right. I'm going to go back really quickly to, to this diagram right in here. This is time on the y-axis right in here, and basically going from northwest to southeast, from the southern tail of the Sierra Nevada into southwestern Arizona. The interesting thing here, basically centered around, in the low 70s to high 60s, is that basically the sediment that we do have preserved, which was deposited after the plateau had basically made its way to the east. It's moving at approximately 100 kilometers per million years. So in 10 million years, it's gone 1,000 kilometers. This is where, it basically looks like there's no spatial dependence on the time in which we have sediment that's being accreted. So very likely your comment that you've made, bears most strongly upon what we see in the western region here. And so from the southern tail of the Sierra, down toward the transverse ranges. This aspect right in here, which I'm associating with basically subduction erosion, probably our interpretation of it is, might need to be refined a little bit by the comment that you made. Anyway, so I appreciate that thought.
Hi, I'm Greg Bartow, and I had a question. Could you expand a little bit more about the slide you showed about the La Honda Basin, the Betano Sandstone, and that was derived from the Southern Sierras, and kind of how that you mapped that out and how that was transported up to the Central Coast. Thank you.
I think this is probably the best summary slide. There are a lot of issues here in terms of the reconstruction of all these rocks. In terms of the showing the former relationship between the Betano Formation and the San Amigdios, the Betano Formation being on Salinia in between Santa Cruz and San Francisco, and the San Amigdio being in the southwestern tail of the Sierra Nevada.
Hey, Marty. Hey, this is Greg again. We can't read those, so if you can explain that a little bit more. We're at a loss here because the slide's pretty small. Thanks.
Okay, yeah, I apologize. On my screens, I see everything in slideshow mode. I think the first thing is to say that previous work by Glenn Sharman, Jared Gooley, and a bunch of other graduate students working with Steve Graham's group at Stanford have established the ties between these sediments. The biggest difference, if you look in the upper right hand, let me see if I can. I don't know if it looks any bigger in this mode right here. Apologize for that. The main point that I'm trying to make here is threefold. First of all, this is the distribution of basement ages shown in black. Basement K feldspar shown in black right in here. This distribution right in here overall is about 5 million years younger than the red distribution, which represents the results from the San Amigdios.
Hey, Marty, you're back on.
Hello? Yeah, is the screen, is the slide not visible or?
One, you hit it from the beginning. So if you go back to slide 41.
Okay, I'm seeing slide 41 right now.
Oh, okay.
I don't know.
There you got it. And now you got the full screen.
It must have been miserable. I'm sorry. Anyway, I don't know if I can completely answer the question, but this black distribution right in here in the upper right-hand corner represents the basement results. The distribution is on average about 5 million years younger than the red distribution, which represents the San Amigdio and La Honda Basin sediments. And so it makes sense that the La Honda Basin and and San Emigdio sediments, which are Eocene in age, would have a somewhat older distribution because they were basically receiving sediments from shallower levels of the crust relative to the present day erosion surface shown in black. And the curve in blue right in here represents what's coming off the western zone of the Sierra Nevada batholith. And it's just incrementally older, but still resolvable from the other distributions. The main thing when you look at this is that the peak in terms of the cooling ages is somewhere in the neighborhood of about 80 million years. And when you look at cooling histories from these rocks, the actual maxima in cooling is actually occurring somewhere in the neighborhood of about 75 million years. And so this is when, you know, the maximum amount of cooling is occurring in the system. And it's also when we have sediments that are most clearly associated or, you know, derived from the region of Southern California that's experiencing shallow subduction. So I don't know if that starts to answer your question, but the restorations of which rocks are adjacent to which rocks is work that has been done by other people. We're just taking advantage of that work.
Okay, thank you very much. We appreciate your time with us tonight, Marty. We wish you could be here in person. We'll look forward to serving you a beer another time.
Okay.
Thanks.
All right.
Okay.
Thanks a lot.
Bye-bye
Okay.
now.
Bye.